Hello, everybody. My name is Samir, and I'm a freelance trainer and consultant for Hadoop, Cassandra, and sometimes OpenStack. In the past year, I've taught about 50 classes throughout the country and in India. And usually in my classes, when I talk about Hadoop, towards the end of the class, I get a very common question, which people ask me, okay, now that we know about like HBase and Hive and Pig, well, how does that compare to MongoDB? Why would I want to use Cassandra instead of HBase, right? So what I wanted to do in this presentation is specifically talk about why Cassandra is different from the other competing NoSQL architectures. So really quick question, how many people here have either installed Cassandra or done a query to retrieve data in and out of it, or are familiar with the architectures like what an SSTable is or a memtable? Okay, cool, so about 50%. What about the same question for HBase? Okay, about 10%. All right, sounds good. So here are the NoSQL options. It's pretty overwhelming, so it's understandable why people ask me this question. It's really hard to know which database to choose for your solution. And every vendor claims that their benchmark is better than their competitors. So the way I think you should approach this problem is first try to identify which one of these categories of databases is correct for your use case. After you've decided upon a category, then selectively choose a specific database. And I'll try to tell you in a vendor agnostic way what I tell my clients for how to do this. 3 to 4 years ago, it was the wild, wild west of NoSQL databases, and it was really hard to tell how to pick one. There were no books, no YouTube videos, and no benchmarks. But these days, I think there are clear leaders emerging in each one of these categories, and there are databases that are dying in these categories. So you should, once you pick a category, you should really pick one of those leaders, as opposed to one of the abandoning databases. All right, so first let me tell you about these categories, and you can be thinking about which use case is correct for you. So we'll talk about key value first. A key value store is basically like a simple hash map, and it's the right use case when all you need to do is access your data via primary key. The API for these type of databases is rather simple. You can basically do a get, a put, or a delete. The key value pairs are stored in a container called buckets. It's different for different databases, but that's a common terminology. You only have consistency per key, so you can't put 2 key value pairs in, and if one of them doesn't get committed, pull them both back out. So atomicity is per key. And these things are usually really fast because they're pretty simple architectures. So very fast lookups, very good scalability. They usually scale with sharding techniques, kind of like MySQL. The value in my example here is a string. It's just a string with sometimes a space inside it. And the key here is an integer. But in these databases, you can actually put any type of data you want in the value. The value is not examinable. So you can't say, give me back all of the keys where the value equals the color blue. Right? You can only say, for this key, give me the value. And the value can be an object, a blob, JSON, XML. And in some of these key value databases, you can also attach a metadata item to the value. So for a name, you can also attach a metadata item there saying, like, this is the age of the person, for example, right? So that's kind of almost getting into key document territory, but think of it kind of like key value for now. The use cases for this type of databases would be things like content caching, web session information, user profiles, preferences, and shopping carts. So here's an ideal use case. Like if you're developing a website, when somebody types in their username and password to log into your website, maybe you have customization done on the front end where the background color can be specific for different users, or maybe the language is different, or maybe the time zone settings will affect how the web page will be rendered. In that case, as soon as the person logs in, you want to very quickly retrieve their preferences for your site and display that HTML and dynamically render it. All right, so in those type of cases where you want a very quick lookup, it's a simple lookup, a key value database is a good choice. Where you don't want to use it is if you need to query by the data type, by the value as opposed to the key, or if you want to do multi-operation transactions, or you need to do some relationships between the different data types. Key document is the other category. MongoDB and Couchbase are probably like the really popular ones here. This is kind of like a key value database, but the value is examinable. And a very common misconception is that in a key document databases, you're going to store documents like Word documents or PDFs. That is not the case. The documents tend to be XML or JSON or BSON, right? Usually I see JSON. And the structure of the JSON or the XML does not have to be identical across the different keys. They should be similar, but they don't have to be identical. So here's a use case that I think exemplifies key document databases. Let's say that you are developing a software that is going to profile children in refugee camps in Africa. All right, so what you do is you like basically go to the camp and you interview children and you find out information, as much information as you can, in hopes of uniting the child back with the child's parents. Right? So in this case, we have a key that I kind of randomly made. It's called one. I know the first name, last name, and location of this child. I know that she speaks 2 languages. I know the mother and the father's name. I know which camp they're in, and I have a blob picture that I put in. Now, for another child, though, perhaps I don't know all that information. This other child is younger, right? So for D, I only know that she knows some Swahili. I don't know who her parents are. So you see how the 2 schemas are somewhat similar, but they're not identical. And in these type of databases, they're very tolerant of incomplete data. And later on, once maybe somebody else in the camp will recognize D and will tell you, hey, by the way, I do know who her parents are, or I know, some more information about her. In that case, you can connect back to that value, and you can append only what you want to it. So the use cases here are like event logging, content management systems, blogging platforms, or web analytics are all pretty good use cases for something like this. And keep in mind that in this case, you don't have to pull the entire value out. In a lot of these type of databases, you can reach into the value and only pick out the specific things you want. If you're going to make a web page with just pictures in it, you can basically only pull out the binary blob of the picture instead of getting the full JSON out or the full XML out. And you can also just update a specific item within the JSON or XML. You don't want to use these type of databases for any complex transactions that are spanning different operations, and you can't really have a strict schema here. If an item is missing, like on the key value on the right, then there's no null stored there. It's just basically blank. So sometimes when you query it, you'll get nothing back. The next example case is graph databases. These are made of nodes and edges. So here is an example. Let's say that you got your hands on millions of metadata records from a phone company. So here is a node. The node has properties attached to it. Over here I have a phone number attached, GPS coordinates for where the phone currently is, and the IMSI number, the International Mobile Subscriber Number. And here's another node with a different phone number. Right? So a node is basically like an instance of an object in an application. And the next concept in graph databases is edges. So edges are also called relations. So here's an edge. They can be unidirectional or bidirectional, but a call is made from one port to another. So I called that number the 415 number. And here is another node and a unidirectional edge to it. And now here is a node that is contacting me, so it's in the other direction. And you can see that these edges have properties, either called or text. And here's a little bit more characters. And you can add more properties to these edges. So maybe I want to keep track of like these edges were initiated perhaps via mobile phones. And this one edge in the middle was done via a landline. And here's some more properties you can add, like a duration of a call to the edge, and the time of the call, the time the call was placed. So the use cases for this is, connected data like social networks, shortest path algorithms, recommendation engines, routing, dispatch, location services. And you don't want to use these for really large-scale examples. Titan is a graph database on top of Cassandra, and Infinite Graph is another graph database that can scale beyond one node. But the complications between the nodes and the relations is pretty complex, and these things usually run on one machine. Neo4j is probably the most popular one here. FlockDB is another one, but FlockDB only lets you query one level deep, as opposed to like Neo4j and other graph databases can let you do a traversal, which is what querying the graph is called. You can do a traversal that says, give me all of the people who are twice removed from the central node. Next, a much more emerging category is real-time, and there's a little squiggly before it because it's technically near real-time is, I guess, the category here. And in this example, I'm talking about Storm. The way Storm works is it's used to analyze the data in motion before you actually even commit it to the hard drive. So the data comes in from a spout. Think of this like an application that you write that connects to the Twitter Firehose via an API, and it's downloading tens of thousands of tweets per second into this pipeline coming into your data center. And then in the very middle, next to the spout, you have a bolt. A bolt is basically consuming the stream, and it is picking out the hashtags. Every time a tweet comes in with the pound symbol in a word, it's picking that out, and it's basically counting the hashtags that are perhaps coming in, or it's every time it sees a specific hashtag, increments a counter for that hashtag, and then stores it in a database down there. So it's taking the incoming stream and making two streams out of it. One of the streams continues onward into a database where you're storing the full tweets, but then the hashtags are being aggregated or counted, and they're going into a separate database. A recent benchmark shows that Storm is very scalable and highly performant. It clocked Storm to be able to process 1 million tuples every second per node. Right? These things can get pretty fast. But these things are very emerging. And I think most of these are in alpha or beta stages, and there's almost no books written on these. Impala and Stinger are a little bit different from Storm. Or here you're capturing the data before it even goes to the database. But in Impala or Storm, you basically do near real-time queries on data in REST that's already in a database. Next, we come to column family. And the main concepts here are that on the left you have rows. Those are the row keys. And in a database like HBase, you're going to actually group certain row keys, like ranges of row keys, into something called a region. All right, so like in HBase, that region 1 through 3 rows will be stored on a specific machine, slave machine 10, and the next region, rows 4 through 6, will be stored on another machine, maybe machine 20 in your HBase cluster. Okay, so region 1 is those 3 rows and all of the column families, all 3 column families for those 3 rows. So, so for row 1, for example, you can see that there's 3 column families we have. A column family is basically just a bunch of related columns. The reason you want to be thinking about how you do the data model here and why would you want to use multiple column families is you want to put data that you're going to query together into a column family. Right? So you kind of don't want to do queries which are going to span column families because each column family is essentially written to a file by itself. Right? So, or here we actually have 2 regions. Let's say this is HBase. We have 2 regions, right? Region 1 is on one machine. Region 2 is on a different machine. Region 1 on that first machine is going to have like 3 files, basically, 1 for each column family. And the other machine will have 3 files, 1 for each column family. And if you end up doing a query across column families, which these databases allow, you're going to have to read it across at least 2 files, and it could be potentially slower. Other reasons to be thinking about column families is you configure usually these databases per column family. So you can put data that's highly compressible in column family 1, And maybe when you query that, it'll be a little bit slower because you got to decompress. But column family 2 is maybe where you want the really high performance stuff, so you don't compress that. And you can, in something like HBase and Cassandra, also the cells are versioned. Now, this is kind of internals to these databases. You shouldn't really be using these versions. So you can do it if you want. There are exposed Java methods, but it's not recommended. This is kind of more of an internal thing within the database. So you could, however, a lot of people do it in HBase, I guess, less so in Cassandra. It's really discouraged. But you can version your data. And when you do the versioning, you can set the version per column family. So column family 1 is compressed and just one version maintained. Column family 2, we're going to do 3 versions, and we're not going to compress it. And if you add a 4th version, it'll override the oldest version. So some people call the data access here kind of like key value. You can think of a key. See that down there? The key is basically like the table name, the row key, the column family, then the column, and then the timestamp. And that will uniquely identify a version of the cell. So that's how you pull your data out. There are no nulls stored here. So one of the good things about these data models is that in column family 1, I have 4 columns, but maybe for row 1, I don't have any. I don't know I don't have the data for those columns. So I don't put anything there. There's no nulls there. Nulls have a real cost on disk in databases or relational databases. So over here, there's no nulls. I only have an XY, so I mean, it's not putting nulls all over the place. So it's good for sparse data models. Perhaps later on, I'll know what the other data columns are supposed to be, and I can populate them in there later. So other things you want to know about these column family databases is you should know your queries up front. And the read and write queries will determine how you're going to do the data modeling. If you're a startup and you think you're going to be changing your queries around all the time, then this is maybe not the best database, because if you change your query around significantly enough, you'll have to change the data model as well. And when you design the data model, I think you really need to know the architectural fundamentals to understand how this engine works, because that's what will guide you into thinking, when you do a read, what's really happening. You want to be able to truly reason about how many disk seeks will occur and what kind of latency you will incur based on the type of reads and write queries you're doing. In a relational database, that's kind of like the black box where it's hidden from you. And as a SQL developer, you're not really thinking about how many disk seeks are going to happen if you do this join, right? But in these databases, you really want to understand the architecture, at least at the level where when somebody gives you their data model and they tell you what the architecture is like for the system, and they say, this is a query I'm going to do, a good HBase developer or administrator will be able to say things like, well, you know what, I'm not going to allow you to run that query because that query is going to put a lot of I/O pressure. It's going to take too many disk seeks, right? Now, okay, that's kind of a background on column family databases, but if you think this is the kind of database you want, how do you pick it? I gave you like 6 examples in that first slide. Well, I think you should pick it based on 3 different things. First thing is, are these databases being adopted? So this is Indeed.com. It's a job posting website, kind of like Monster or Career Builder. And I typed in a bunch of column family databases into here. And we can see very clearly that if you pick Accumulo or HPCC or Hypertable, you're going to be in a very small club, right? If you pick HBase or Cassandra, the orange is Cassandra and blue is HBase. You can see that they're really getting adopted and they're really close to each other. So this is basically saying that, well, you probably won't go too wrong if you pick either or. These databases will not be abandoned, basically. The 0.06 means that in 0.06% of all job listings on Indeed.com, HBase or Cassandra is basically showing up as a keyword. Other thing you can do is go to Google Trends and type in Cassandra and HBase. And if you just do that, Cassandra will be way higher because of Greek mythology. So you want to actually go to the left side of this page, and you can narrow it down to computer and technology field. And then it will do somewhat of a better job. But even here, you can see that it's saying that like Cassandra was getting a bunch of queries under databases or computers and technology. But Cassandra didn't exist in 2005, right? So I mean, you should maybe be thinking that maybe up to here, this level right here, might just be other people searching for other Cassandra-related stuff, and it's kind of like a skew, you know. So this stuff down here is kind of skewed, I think. And these databases were invented around this time. This is when the world found out about them. This is when queries started to happen. And I was trying to figure out what this spike was. This is when, because around the time Cassandra became a top-level Apache project, so maybe people just kind of got a bunch of press releases. This is showing Google Trends search volumes in different countries. I found it kind of interesting that, first of all, South Korea, there's something happening in South Korea. They're like doing the most Hadoop and Cassandra and HBase searches. So it's really interesting. And then this left is Cassandra. It's adopted more in India than, and over here you can see that HBase is adopted more in China. And India is kind of after Taiwan down here. So China prefers HBase, and India seems to prefer Cassandra. Another thing you can do to decide which database you're going to use, do your due diligence by going to the Apache user groups. And this is the activity on the Apache user mailing list. You can see that in May 2013, there were about 567 messages on the Apache mailing list, and HBase is somewhat similar. So, I mean, these two databases are kind of neck to neck right now, right? So how would we actually go a little bit deeper to pick one? A little bit of background. Cassandra comes from, its origins come from two white papers. November 2006, Google published a white paper called Bigtable, and October 2007, Amazon published Dynamo. And then I think a couple of years later, basically Facebook took the storage engine out of Dynamo and married it to the data model of Bigtable for their inbox search application, and they open sourced the Cassandra database and put into Apache. They kind of somewhat abandoned it, and they adopted HBase much more heavily these days at Facebook. But Jonathan Ellis, the CTO of DataStax, was the first non-Facebook committer to Cassandra, and he's brought this database very, very far from its humble origins when it was first released. This is HBase. It's kind of, this is actually Hadoop, right? So Hadoop origins are 2003 Google File System paper. Basically is implemented, 95% of that architecture is implemented as HDFS in Apache. MapReduce, the white paper becomes Apache MapReduce. Google did all of this coding in C++, released the white paper architectures, but no code. It was up to companies like Yahoo and later on Facebook, Twitter, and a bunch of other companies to implement the ideas of these white papers in Java, which they found to be a more robust language than C++ because of its garbage collection and handling of memory leaks. So both of the, HBase specifically, by the way, was started in 2006 by Chad Walters and Jim Kellerman at PowerSet, which was later acquired by Microsoft. And right now there's a lot of committers to these databases. You can actually go to Apache and you can find out who the people are who have privilege to actually write the code in Apache. If you're going to get tech support from like Cloudera or Hortonworks and you don't know who to go with for your vendors, find out who's employing the software engineers who are actually committing the code. Right, so go do that. And these Apache projects show you exactly who's writing the code. Okay, both Cassandra and Apache are written in Java. They're column-oriented databases. They've been proven to scale to more than 1,000 nodes in production. Very low latency reads and writes, meaning probably under 100 millisecond reads and writes. They use this idea called log-structured merge trees, which I'll talk about in a minute. And they're atomic at the row level, so you cannot like lock 2 rows and like shuffle data around. You can only lock 1 row. If you want to lock 2 rows, you'll have to do it at the application side and then release the lock there. There's no support for joins, transactions, or foreign keys in both of these databases. Now, they differ. Cassandra is more of a peer-to-peer architecture. HBase is master-slave. All the Google stuff was done in a master-slave idea, where if the master node goes down, then everything kind of goes down. But these days, there is more high availability in the Hadoop world. Cassandra comes from Dynamo, and Amazon did a purely peer-to-peer architecture, no master slaves. Cassandra has tunable consistency. HBase has strict consistency. I'll talk about that in a bit. Cassandra has secondary indexes natively available. HBase does not. There are tricks to be able to do it in HBase. Cassandra writes the incoming data directly to the Linux file system, like ext3 or ext4. HBase writes it down to HDFS. Conflict resolution during in Cassandra is handled during reads, and conflict resolution in HBase is handled during writes. And we'll talk about the other ideas in a minute. All right, let's just think for a second why Amazon invented the Amazon Dynamo database. So if you read the white paper, their use case was they wanted to make a shopping cart service that will always allow people to add data into the cart. They never wanted to be able to reject an item that somebody added on their website to a shopping cart, no matter what. No matter whether there are hurricanes taking down data centers or power outages or disk failures or network failures, they needed that right to be successful and not lose revenue on that sale. If there's two conflicting versions of a right, then Amazon wanted this Dynamo database to be able to pull both conflicting versions. So if somebody basically logged into the website from their browser on their computer and they added something to their shopping cart, and then they logged in from their iPad and they added something else to the shopping cart, perhaps there's conflicting things in their shopping cart because they're logged into both, then what happens is when you go to the checkout, Dynamo will go read both conflicting versions of the items and merge them together and give that back to you. You can do different things. You can also, if there's conflicts, you can look at them and you can only look at the timestamp and pull and basically throw away the old timestamp data. So you have the options of what you want to do. This database Dynamo was designed for applications that need tight control between the trade-offs between availability, consistency, cost effectiveness, and performance. Other things they used Dynamo for was bestseller lists, customer preferences, sales ranks, product catalogs, and service management. Now, Google designed Bigtable mainly for keeping the entire web crawl cache data. They were basically doing a distributed parallel wget and downloading the HTML into Bigtable, into a column in Bigtable. And that was its own column family with one column with HTML files. And then they were basically doing a MapReduce job against that column that would derive statistics and metadata out of each HTML file and then populate a different column family with metadata. This is an English language. On this row number 2, it's English. And the geography is, this is UK English. And it was last updated at this time. And all this information goes in other metadata column families, which are not compressed. But Google compresses this first column family, which is all HTML. It is highly compressible because it's all text data. At one point in time, Google used Bigtable for many different products: Gmail, YouTube, Google Earth, Google Finance. And even though HBase is almost a clone of Bigtable, in recent years, the architecture has started to diverge. The Bigtable white paper came out in 2006. We are 6-7 years away from there. And even though the early prototypes were a clone, now it's kind of becoming a little bit different. And Google also designed Bigtable to be able to handle a variety of workloads. Sometimes they wanted to be able to do high throughput, batch processing jobs, and other times they wanted to be able to do really latency sensitive serving data to serve a real website. So it's kind of a diverse database. It relies on an underlying Google file system to do the replication of the data, and we'll talk about that in just a minute. And they also have strong integration with MapReduce. This is the Cassandra model. We have 8 nodes in a ring here. Each node will have multiple hard drives. One way that Cassandra realizes the health of the different nodes is through a protocol called Gossip. Gossip runs on every node every second. And when a Gossip protocol runs on a node, it will contact 3 other nodes. And it will basically share information with those 3 nodes about its own health and health of other nodes it's gossiped with in the past. So basically, if node 4 gossips with node 8, node 4 might tell 8 a bunch of stuff. Hey, by the way, a few seconds ago, me, 4, I talked to 3, and actually he didn't respond back. So 8 will be all right. And then maybe 5 will talk to 8 the next second, and 5 will gossip with 8 and say, I was able to talk to 3, right? But 4 was not able to talk to 3. So 8 now basically has a suspicion level on node 3. Is node 3 up or down? Well, it must be up because node 5 was able to talk to it, but node 4 was not able to talk to it. So now node 3 is suspicious. But see, this is a more advanced way of determining the health of nodes than a simple heartbeat, where if a heartbeat doesn't come, the node's probably dead, right? But in this case, it's more interesting because with the gossip, maybe just the network connection between 4 and 3 was having a problem, the switch. But 5 to 3 was fine. So node 3 is not down, and node 8 can trust that 3 is still up. It's just 4 can't get to it. The way the actual failure detection happens is this Japanese protocol called fee accrual detection, which allows you to set a suspicion level on a continuous scale on nodes to suspect whether they're down or not. HBase doesn't do this. HBase is a little bit different architecture. So HBase has a lot of moving parts. There's master machines and slave machines. The green name node is the master of the file system. And you can see that the master of the file system has a slave component called the data node on each node. The data node heartbeats with the name node every 3 seconds. And each data node is telling the name node, I'm up and running, and these are the things happening from a storage and perhaps a network perspective on me. And there's the HBase master. You have a standby HBase master as well, and there's a standby name node. And the HBase master actually does not heartbeat with the region servers. The slave component on each slave machine here is called a region server. A region server is basically storing maybe 20 to 100 regions. Remember in the previous slide we had rows 1 through 3 was a region, and that region actually was made of 3 column families with 3 files coming out. Well, you basically put something like 10, 20, maybe 100 regions on each region server. All right. You have to have Zookeeper as well, and Zookeeper should be run on an odd number of machines, so leader election will be able to work. If you have 4 machines, 2 can say one thing, 2 can say another thing, and that can cause problems. So run an odd number of machines, 3, 5, or 7. You can start with 3, and sometimes you'll also need MapReduce if you want to do like full table scan. So now you need a job tracker as well. There's no high availability for the job tracker right now. And now you have a task tracker running on each machine, which will launch daughter JVMs for maps and reducers to actually run to do the table scans. So you have a lot of moving parts here. You have a whole bunch of master machines if you want to be able to run this in a highly available manner. On the slave machines, each one of these components is a JVM running with its own heap, and the task tracker is launching a bunch of daughter JVMs, maps, and reducers. So and you got Zookeeper up there. So learning this architecture is going to take more time. It took me like 6 months to a year to learn HBase, but maybe only a couple of months to get comfortable with Cassandra. Heartbeats from the region server go to Zookeeper in HBase. And then Zookeeper will tell the HBase master if there's a problem with one of the slave machines. And then the master will take the decision to actually do something to recover from a region server's failure, or maybe just one disk crashed and some regions got lost. HBase master will help take care of that problem. So I mentioned effort to deploy. These are just some more information on that. Really quickly, I'm going to talk about how a write happens in HBase. You have a client there. Client's going to contact Zookeeper and say, where is the root table? So the client wants to write row 500, okay, and some column in row 500, but client doesn't know where the region is being hosted on the slave machines. Client goes to Zookeeper, says, where is the root table? Zookeeper says the root table is on this machine over here. The client goes to that machine, pulls the root table out, and now the root table is on the client. That's what the root table looks like. It doesn't show where row 500 is. Basically, you go to the root table, you say, where's row 500? It says, well, you need to go to meta 2 for that. You got to go to this other table, meta 2. He should know where the region actually is. So now the client is going to basically query the root table, say, where is row 500? Meaning, rather, where is the meta table that knows where row 500 is? And then the root table says that it's over there. That's the meta 2 table. And then the meta 2 table is basically pulled in to the client as well. And then the client queries the meta table and says, okay, where is the region that has row 500? And then the meta table actually tells it that. And then the client goes to the specific region server, which is hosting the specific region out of hundreds of regions for row 500, and maybe the regions, maybe also the rows above and below it, and it actually sends that X, that write, to that machine. And then what happens is underneath of HBase just sends it from the HBase JVM down to the data node JVM for HDFS, and then it's the HDFS file system's responsibility to do a synchronous replication from that first machine to another machine in your Hadoop cluster, and then another replication happens. So the default replication factor in HDFS is 3. This is a synchronous replication.
Second one is not synchronous?
Well, no, it happens in a pipelined way. So the HBase just writes to one machine. It's HDFS' responsibility to take that write and replicate it in a pipelined manner to 2 other machines to achieve the replica factor of 3. So the thing is, and then basically after that happens, then HBase is going to, the HBase region server there will tell the client, okay, I'm done with the write. So it's a synchronous write that just happened underneath of HBase. There's no control or the replication for each write or consistency for each write. You can just kind of set that for the entire thing. And these root and metatables are cached, so it's never going to have to go back to Zookeeper for the root. And eventually, it will learn about all the metatables. And then in the future, when the client does a write, it's just going to go directly to a slave machine. It doesn't have to keep going back to Zookeeper. And Cassandra is different. You guys have probably seen this before. In Cassandra, when the client does a write, it does a write, let's say, with replication factor 3, consistency level 1. So the client will randomly pick a machine called a coordinator machine. It doesn't have to be 7, but it is in this case. And then the coordinator will say, okay, you want to write with the replica factor 3? Okay, I'll send it to 3 different machines. Basically, the row key gets partitioned with mummer hash or MD5, and whatever long number comes out of the hash will determine which machines it will go to. And the replica 1, 2, 3 is now sent to 3 machines. And consistency level 1 means that as soon as one machine responds back and says, I got the write, then the coordinator will continue on with the client and give the write successful. And the other 2 writes are still going to be implemented, but it's just, it's not holding up the write. But if you want to hold up the write, you can a little bit more. So now we're doing replication factor 3 write, just like before, but we're saying we want to get the write committed to at least 2 machines because of some, Garmin, Sarbanes-Oxley, right? And then after 2 machines respond back, then we tell the client we're done. This is flexible, so you can do replication factor like 4, right? 4 writes get sent, and consistency level is 2, and then you send it back to the client. So this is a really important thing to understand about the differences. Cassandra has, tunable or elastic consistency. Now, here's the thing, though. When you do the read from Cassandra, if you want to guarantee strong consistency, you have to do the read from at least 2 nodes. So you write to 3 nodes, right? And then you have to read from at least 2 nodes. So when you write to 3 nodes, you basically write with like consistency level 2. So you definitely wrote to at least 2 out of 3 nodes. And then when you read, to make sure you got the newest update, to make sure that you're not getting that 3rd update that might have not been finished in the write, to do the read, you have to read from 2 nodes, right? And then as long as 2 nodes agree, then you'll get the response back. In HBase, when you do the read, to guarantee strong consistency, you only have to read from 1 machine. Some region server is responsible for that region, and only that machine can respond back and give you back that write. Those other 2 copies are dormant, and they're kind of like hidden in HDFS. Unless that first machine crashes, you don't read from those other 2 places at all. You can only go to 1 machine to do the read. So to get strong consistency in HBase, the write was already strong, right? And the write was maybe a little bit slower as well because you had to wait for all 3 to happen. And when all 3 happen, in HBase, you can choose whether you really want all 3 to go to disk. The first one will definitely go to disk. The second and the third can you can configure so it'll go in RAM and then eventually get flushed later. Or for the second and third in HBase, you can force it to go to disk as well, which will be a little bit slower. All right, we have about 10 minutes left. Let's see how much more I can cover here. This is an idea called log-structured merge trees, which comes from Bigtable. We have a key there, like before, and we want to write this value x. We've already found the actual region server in HBase, and we've already located the node in Cassandra, okay? This is the node that we want to do the write on. Okay, the write comes to this node now from either the coordinator machine in Cassandra or from like the client in HBase. All right, and it comes into a JVM. in both Cassandra and HBase. Blue is going to be HBase and green will be Cassandra. From the JVM, the write gets kind of duplicated to two places. It goes into something called a commit log or a write-ahead log. In Cassandra, you call it commit log. In HBase, you call it write-ahead log. So the Z went into there. And this is a sequential file. So if you're using a spinning disk, you're not doing a disk seek. You're just writing to the very end of the file, right? And usually spinning disks can write like sequential throughput, like 120 megabytes per second. It's pretty good. And then the JVM also sends that Z write to something called a memtable in Cassandra or a memstore in HBase. The what? Yes, that's why it's the same color as HBase up there. And green is commit log for Cassandra. All right, so that memstore is usually a 64 megabyte memory buffer. The write is persisted to disk. You know it's safe. And it's in a memory buffer. As soon as those two things happen, you'll basically give the write successful back. All right, then what happens in the background is if you're using HBase, remember this is only one node the write always comes to. So you got to do that synchronous replication into HDFS. With Cassandra, remember the write went to two other nodes already, so you don't have to do that kind of thing. That's the client already sent it to two other nodes, and the two other nodes wrote it to their own commit logs. All right, then that memory buffer is eventually going to get more data coming in because more writes will come in. The 64 megabyte memory buffer will get full. When it gets full, it gets flushed to a file. The file is called SSTable in Cassandra or HFile in HBase. And remember, in HBase, you still have to then replicate that synchronously to 3 different places. And for every column family in these databases, you'll have a different memstore. So this is an example right now of a table with 2 column families. And you see the first column family is flushing to its own file. The other column family is flushing to its different file. And when these flushes happen, this is a flush. And in the file, you actually also maintain a Bloom filter and a block index. In Cassandra, you can only do a row-only Bloom filter. In HBase, you can do a row or column Bloom filter. And what these things are doing is, by the way, in HBase, the HFile is what that's called. The HFile has the block index and the Bloom filter in that file that gets flushed. In Cassandra, you actually have like 3 files. So you have like 1 file with the data, 1 file for the block index, and like 1 file for the Bloom filter. And the reason you have that is because imagine that these flushes keep happening, the memory buffer keeps getting full, and you have like a bunch of SSTables now. And the reason you have a Bloom filter is because like when you have 10 SSTables, how do you know where row 500 is? So the Bloom filters are all stored in memory as soon as you reboot the node. It goes into memory, and then really quickly, when you want to do a read, you first go check all those Bloom filters in memory and say, hey, which SSTables have the row 500? And maybe 1 or 2 of them will say yes, and then you go directly into the SSTable, and then you check the index really quick to see where in the file it is, and you go pick it out of that file. You do a disk seek into that file, and then you actually pull it out. All right, now in Cassandra, you can flush per column family. So remember I had 2 memstores there? They can individually get filled, and when one of them gets filled, it'll get flushed. All right, so 1 column family got full, memory buffer, it got flushed. But in HBase, if 1 flush happens for a column family, all the other memstores will get flushed as well. So maybe 1 column family has like pictures you're storing in it, and other column families are just like tiny metadata stuff, so it's not getting full. But when you fill up this memstore with the pictures, now you're gonna have to flush the other ones as well. And this will probably put a lot of memory pressure on you because you're flushing these little tiny files, synchronizing them with HDFS or the network. There is work being done in HBase to, under JIRA 3149 to do the flush per column family. Secondary indexes are natively supported in Cassandra. You want to use a secondary index in Cassandra when your column has a certain key or certain value that's showing up multiple times. So like this is like a secondary index is a good use case for like if you have a column that's storing states. There's only 50 possible values and you have a billion rows. It's good choice. But if you're storing email addresses in that column, don't put a secondary index on there to query it out, right? Use different techniques. No native secondary index support in HBase, but there's the idea called triggers, where when you update a value on a cell, you can cause a trigger to be launched to go update another column family where you're doing like a poor man's secondary index with another column family. You're like rolling your own index, basically. So it's possible to do that. in HBase as well. It's just a lot more effort and work. SSD support. So I have just a few more slides. There's a really good talk by Rick Branson. It's 13 minutes long on YouTube about SSD support in Cassandra, so check that out. One thing you can do with Cassandra, though, is you can actually put, you can put like the SSTables, those flushed files on SSD, but you can put the commit log on spinning disks if you want. You can choose. In HBase, you can't really do that, because HBase is kind of dumb as far as the file system goes. HBase just hands the right to HDFS. And then HDFS is responsible for putting that on disks on its own machine and other machines. And in HBase, you can't really separate the commit log to go, or the write-ahead log to go on SSD, and like the flushed files to go on spinning disks. You can't really do much control there. However, the MapR and Intel distributions of HBase are starting to make some effort in this field. And in the HDFS, those two JIRAs, there's preliminary discussions happening for being able to decide where you're going to put the file, whether it's going to be on an SSD on a node or a spinning disk. Compactions, I'm not going to talk much about this. I'll just tell you that in Cassandra, you can do tiered and leveled compactions. In HBase, you can only do tiered. If you want to learn more about what a compaction is, check out that talk from that blog from Jonathan Ellis. Reading after disk failures. In Cassandra, if a specific disk fails, and that happened to be the disk that had the data you wanted to query, it's not a big deal, because when you do the read, you're not going to that machine necessarily. You don't know which machine it is. You just kind of randomly pick a machine that's now the coordinator machine. And that coordinator machine will do like a hash of the key, and it'll know which 3 machines to do the query from. And if one of the machines can't respond, it doesn't matter. One of the other 2 will respond. In HBase, if it's only one machine who can do that read, because that's the region server responsible for that region. So if a disk fails, that region server is going to basically have to get the data from one of the other 2 machines or the network, then send it back to you. So perhaps after disk failures, HBase will respond a little bit slower than Cassandra will. 2 more slides, I believe. Data partitioning. In Cassandra, when you are writing your table out with the row keys, you can do either ordered partitioner or random partitioner. Random partitioner means that like you put row 1 in there, then row 200, then row 3, then row 500. It's just random. And you don't get any hotspots when you do that, because you're kind of spreading your writes across all of the nodes. In HBase, if you're just doing integers for the row key, you're going to only be hammering the last node. Whichever machine has the region at the very bottom, that guy is going to get hammered. And you're not spreading your writes across, because the stuff up there is all ordered, and those regions are not being touched. So in HBase, you very commonly will actually take the row key you want to write, and you'll actually do MD5 hash or something of it. Then you get the MD5 hash and append it to the beginning of the key, and then you send that into HBase. So now the key is kind of going to a random machine, and you're not getting a hotspot on just one machine. But it depends on your use case. So sometimes an ordered partitioner does make sense, but you should know for Cassandra, like 95% of use cases, use the random partitioner, not the ordered. All right, you have 3 more minutes. Triggers and coprocessors. This is under development for Cassandra, but it already exists in HBase. What this lets you do is basically send client-supplied code into the address space of the server to run. So basically, you can do something like every time you have a special column family, and you say, like, look, anytime anybody does a put in this column family, I want you to also run this other logic to do something else, and that all happens in the CPU of that machine. So you can say, anytime anybody does a put in this column family, I want you to also do like something like increment a counter in a different column family. Compare and set is under development for Cassandra, but it's supported in HBase. This is basically like an atomic read, modify, write. It's also called compare and swap or check and set. And finally, multi-data center support or disaster recovery is significantly stronger in Cassandra. It's very mature and well tested. See, initially when Cassandra was developed at Facebook by former Amazon Dynamo engineers, Facebook needed multi-data center support. It was a global company with the data stored all over the world, and you don't want to have European users doing a query to a data center in like Virginia. The latency is too high. So they needed multi-data center support. So that was kind of one of the core things built into Dynamo and Cassandra from day one. Rackspace is also a big contributor to Cassandra because of its multi-data center support. So with Cassandra, you can have a recovery point objective be 0, meaning you can rest assured. It'll be a little bit slower to do these type of writes because you're setting the writes to both data centers, but you can do the write where you say, I need the write to go to both data centers and go to disk on both data centers, and only then go and tell the client that you did the write. In HBase, the replication is only asynchronous, so the recovery point objective cannot be 0. You might lag a few milliseconds, seconds, or minutes behind. In Cassandra, you can do synchronous or asynchronous replication to the other data center. All right, we are at time. Since I'm freelance, I can open source my slides completely. They're available at that link under Creative Commons. That's my email address. I'm also authorized DataStax training partner, so I can teach DataStax curriculum. You can shoot me an email if you're interested in getting any training classes from me. I do custom consulting and training. I used to work at Hornworks, Accenture R&D, and Symantec. You can find me on LinkedIn, Twitter, and there is a YouTube video I have as well. Thank you.